Hello, welcome to my talk on Pi Stories in Computer Age. Can we have enough digits? This is the third part of the series talk. In this talk, we'll make a short introduction on Pi digit hunting in Computer Age and why we are still doing this. And then the introduction on Ramanujan's 1-over Pi series and how it gets accepted. And then we move to new faster Ramanujan type series and other new series for Pi. In the history of the digit hunting for Pi, it is started from very early stages, even back to Archimedes, the first stage of the digit hunting for Pi using polygons. In 1630, 38 decimal places had been calculated for Pi. And then, in 18th and 19th century, arctangent functions were widely used for calculating Pi, and the decimal places increased from 100 digits at about 1700 to 527 in 1873 and to 620 in 1956. Now, since the mid-20th century, computers are used to calculate Pi. In 1949, the first computer Pi decimals would be 2037. And now it moved up rapidly 31.4 trillion decimal places. This was presented by Google on the Pi Day in 2019. So in reality, if we use Pi for calculations, we can see the simplest Pi equaling to 3, and then we would have error about minus 4.5%. If we use the most conventional Pi, 3.14, and the error would be minus 0.05%. If we apply Archimedes approximation Pi equaling to 22 divided by 7, the error would be smaller. It is about 0.04%. And a better approximation can be obtained if we use 4 decimal places for Pi, 3.1416, and the error would be 0.0002%. So this would be very accurate for most applications. In NASA's Jet Propulsion Laboratory, 15 decimals is used for Pi. To calculate the farthest spacecraft, it is about 12.5 billion miles away. The error would be only a couple of inches. If we apply 39 decimals, which was already obtained in the 17th century, this used for the visible universe, it is about 289 billion light years. The error of the calculation would be roughly at the diameter of a hydrogen atom. It seems when Pi is approximated to 39 decimal places, it would be accurate enough for any calculation. But why people are still doing the digit hunt for Pi? The main reasons for this would be this is the good way for testing the speed of a computer. And search the pattern whether all digits 0 to 9 would appear evenly in the Pi digits. seeking faster ways for calculating more decimals for pi. This can be seen in the earlier method used polygons before 18th century, and the arctangent series in 18th and 19th centuries. But now new development can be seen in 20th century and beyond. The new development including the new series for pi and faster computers. Srinivasa Ramanujan was an Indian legend mathematician who had almost no formal training in mathematics, but in his short life, he made substantial contributions to mathematical analysis, number theory, infinite series, and continued fractions. In one of his notes in 1914, he presented a very strange series for 1 over pi with no proof, given in a formula as this. Obviously, such a complicated series with no proof would not attract much attention. This lasted more than 70 years, and then things were dramatically changed since 1985. What happened in 1985 was Ralph William Gosper used the Ramanujan series to calculate pi to 17,526,100 digits for pi. This was the world record for pi decimals then. And after the check against other calculations of pi, the Ramanujan series gave all correct decimals. Therefore, it was suggested that Ramanujan series would be correct, not an approximation. However, a proof was still needed. Later, it was shown each additional term of this series would add roughly 8 digits to pi from Peter Bowen, the reference. And now the Ramanujan type series are the main series for calculating pi using computers. Then an important event was in 1987. The Bowen brothers, Jonathan and Peter, proved the Ramanujan series of 1 over pi. This actually started a new era for pi calculation. Since then, we can see more rapid series for 1 over pi have been proposed. We can see this in the following slide. The digits for pi increased quicker. In 1987, pi digits reached 100 million, and in 1989, it is 1 billion. In 2002, 1 trillion digits for pi. In 2011, we have 10 trillion digits for pi. And in 2019, we have 31.4 trillion digits for pi. In 1989, David and Gregory Chudnovsky produced a similar but more complicated series for 1 over pi to the Ramanujan series. This series given in this form. So when we compare this series and the Ramanujan series, we can see the new series is more complicated. And based on the reference for this series, each additional term would add roughly 15 digits to pi, while the Ramanujan's series would add 8 digits to pi. In 1993, Bowen brothers extended the Ramanujan series to a general form given as this. Here we have the constants C, A, and B. So by setting the constants A, B, C correctly, different series for rapid calculation of pi could be produced, and the sum can be extremely fast. One of the extended Ramanujan series given by Jonathan and Peter Bowen in 1993 is given as this by the constant C, A, and B. But if we look at the digits for the constant, here we can see 47 digits. It is very complicated, and these digits take me about an hour to get all these digits correct. And for this series, each additional term would add roughly 50 digits to pi. So this is the significant advancement for calculating pi, how fast it would be. But it must be noted, for such long digits, the conventional programming might not work. In 1996, Bailey, Bowen, and Prof present a new series for calculating pi, given in a quite simple form as this. And if we calculate pi, we can see the first term when n equal to 0, we have 3.13333. And if we add the second term, we could have 3 digits correct for pi. And with the third term, we have 4 decimal places for pi. So we can see when n equaling to 6, we can get 10 decimal places for pi. And one advantage of this series would be the similar transform 16-base system to 10-base system. For instance, if we have 3.14 in 16-base system, if it transformed into a 10-base system, it calculated as this 3 times 16 power of 0. So 3 from here, and 0 is the first term, similar to here. The second term is 1 times 16 power of minus 1, and 1 from here, and n equaling to minus 1, similar to this term when n equaling to 1. And the third term, 4 times 16 power of minus 2. So this equivalent to n equal to 2. So the result for this would be 3.078125 in 10-based system. That is the value we are using daily. If we compare this series, we can see some advantages in calculating pi if the calculation is in the 16-base system. So for calculation in a 16-based system, we don't need to calculate all the terms. Here, we only calculate the value in the brackets for each n. And when add the calculation value together, we can shift the value by 1 place to right when n is increased by 1. So the value before the bracket 1 over 16 power of n is essentially the factor for transforming the 16-based value to a 10-based value.